Good afternoon, everyone. First of all, it's our pleasure to have had the chance to participate again in this conference. So, we would like to kindly pass our appreciation to the Symposium Committee and to University of Bahrain for this opportunity. I'm Sarah Boudouh, an assistant professor at University of Lagos. In this presentation, we will have a sneak peek to our work titled Leveraging Distributed Data for Glaucoma Detection, a Federated Learning Approach. Now, in this presentation, we'll start first with an introduction, and we'll pass to our proposed approach. Afterwards, we'll discuss our results or our obtained outcomes, and finally, we'll have a conclusion. Now, glaucoma is a long term eye condition that damages the optic nerve. It is the leading cause of vision loss worldwide, and based on the World Health Organization, by 2040, the global glaucoma population is expected to reach 111.8 million cases. Now, color funds images taken with funds cameras show detailed rental structures like the optic disc, macula, and blood vessels in full color. They are essential for diagnosing and tracking conditions like macular degeneration and glaucoma, providing critical information for eye treatment. AI and deep learning approaches have merged as transformative tools in ophthalmology, with numerous studies leveraging deep learning models to address challenges such as glaucoma detection. While these models show promising results, several challenges still need to be addressed. Highlighting one of these approaches, federated learning is a decentralized machine learning approach where multiple entities collaboratively train a shared model without sharing their local data. Of course, this ensures privacy and security. Now, diving further into federated learning in glaucoma detection, it enables collaborative model training across institutions without disclosing patient data, hence protecting privacy. It uses a variety of datasets to improve diagnosis accuracy and flexibility across populations. Now, federated learning have three main categories, starting with the first one, which is called horizontal federated learning. It is applied when datasets from different entities share similar feature spaces but belong to different users. We are going to take an example. If we have two or multiple hospitals, both or all of them have eye scan images of their patients, and these scans are used to detect glaucoma. Now, the type of the data is the same, however, the patients are not the same. The second kind is a vertical federated learning. Now, it is used when data sets have different feature spaces but overlap in user ideas. Which means a hospital has, for example, eye scan images, while an insurance company has patient health records. These data sets, or these two different data sets, are combined to improve glaucoma detection, where we can notice that the type of the data is different, however, the patients are the same. Finally, we have federated transfer learning. It is suitable when data sets have different feature spaces and little overlap in users. So, for example, we have eye scan data from one country and general health records from another country are combined to train a model that works better globally. Now, in our study, we propose a horizontal federated learning approach that enables collaborative training on diverse data sets while handling variations in data preparation, improving or aiming to improve the model's ability to work across different populations. Now, in our proposed approach, the process of federated learning starts with sending the initial global model to the three clients, which are in our case the hospitals. And then every client starts the training process using its own dataset. However, the hyperparameters were the same for each client. After the end of each client's training process, the new weights of each local model were uploaded to the cloud. leveraging, of course, cloud computing. The central server in the cloud aggregates the received weights from all the clients. Now, the aggregation is actually an average process, and this averaging process starts where in each layer we calculate the average of the weight from the three local models, and a new global model is created that is initialized or initiated with the average weights. After that, the new global model is sent back to the clients for a new round. Now, the stopping condition uh, was based on the global model evaluation phase. Each dataset was split into training and testing sets. All the testing sets from the three different clients were collected for the global model to or for a evaluation after the end, of course, of each round. Now, in the simulation phase of this study, more than 20 glaucoma datasets were collected to ensure variety and maximize the volume of data used for training and testing purposes. These datasets were distributed across various clients, to be more specific, three clients, in a federated learning setup. The figures provides a visual representation of the diversity of the selected samples. Now, meanwhile, this table outlines the distribution of datasets across the clients. Looking at the table and the number of samples, we can notice the difference among the selected datasets. The dataset imbalance in our simulation reflects the challenges of real world scenarios where the availability of data from clients, which are hospitals, depends on their patient demographic and record volumes. Achieving a perfectly balanced dataset across clients is unrealistic, as some hospitals may have significantly larger or more diverse patient populations than others. Additionally, the use of data sets like the collected ones, the various and the SMDG 19, which contain only preprocessed glaucoma samples, by the way, was necessary because these collective data sets were already curated and did not include non glaucoma classes. Of course, when you say non glaucoma classes, we are talking about other diseases, not normal samples. This limitation, while introducing imbalance, mirrors the practical constraints in real world application, where institutions often contribute data based on their specific research focus, or more specifically, based on their clinical practices. Now, moving to the proposed global learning architecture. Of course, the data was images, so the architecture was a convolutional neural network kind based on transfer learning techniques. The global model was inspired by the VGG16, starting with an input layer of 229 per 229 size. Afterward, VGG16 was used as a feature extractor. The phase included four blocks, all initialized with ImageNet weight and frozen, since not freezing them did not achieve great results as the opposite. Moreover, the classification phase included one block mainly focusing on the multi-layer perceptron algorithm with 512 neurons and ReLU as an activation function. Finally, one output with a sigmoid activation function, since the classification was binary and the classes were glaucoma and normal. Now, the simulation was done using TensorFlow 2.10 and Python 3.10 in a machine with an NVIDIA GPU GTX 1660 Super. The simulation included four rounds in each one, and for the three clients, a 50 epoch training process was done using each separate dataset. Using the total testing set, each round was evaluated, as we've mentioned before. As shown in the table are the hyperparameters and the three, of course, metrics: accuracy, sensitivity, and specificity. They were selected for the evaluation phase. Now, during the evaluation process, we can notice the improvement of the global model as demonstrated in the confusion matrices. Now, we can notice that drop on false positives and false negatives over time and the increase in the true positives and true negatives. Now, however, since the averaging was based on weights that have been trained on completely different sets of data, we can notice as well the decrease in the accuracy and recall for some clients starting from the second round, which is R1 here. Yet, the increase did not have a big influence on the global model outcomes. The opposite was, of course, expected since the approach was based on federated learning. Furthermore, diving further into the averaging process, which was based on an equality averaging between the three clients, we can notice that client 3 had the biggest data set, as we've seen in the previous table. Hence, the obtained weights of the third client are more valuable than the other clients, of course, data set size wise. Therefore, in the last round, a separate evaluation phase was added in order to investigate this issue. The confusion matrix of the fourth round, R3, where the averaging process including clients' datasets, bondage leveraging client 3, in which in each layer the third client weights were favorized by using custom weighted Fed average. Since in the first trials we used unweighted Fed average, so it was just basic averaging, we can notice the improvement in the accuracy and recall, which were boosted from 96.78 to 97.22%. On the other hand, compared to existing studies, we can notice that when federated learning is applied, the maximum accuracy reaches 95.41%, even though their model included the usage of VGG16 alongside ResNet 50, which we used as feature extractor, yet the focus on including several different data sets and leveraging the size in the averaging process and the aggregation process was the reason of the better accuracy obtained in our approach. Meanwhile, for the approaches that included a single model, we noticed the superiority of the proposed approach. That was, of course, due to the federated learning process nature and the fact of obtaining knowledge from different data sets and using them instead of just one training process. Now, to sum up, the study proposed a federated learning based approach for glaucoma detection using transfer learning, uh, of course, improving performance through federated rounds. The weighted averaging mechanism addressed data set size disparities, boosting, of course, the accuracy to or into 97.22%. The results highlight federated learning's potential in medical imaging, suggesting future work on adaptive weighting and broader disease applications. So, thank you for your attention and happy to answer any of your questions.